So today we're going to talk about concentration of individual ions. To do this, we're going to talk, when we talk about ions, we're going to talk about ionic compounds, of course. That's what we're going to use here. Remember, there's a term that goes with this particular lesson we're going to do today. For ionic compounds, when you put them into water, they undergo the process of dissociation, right? So dissociation, ionic compounds. What's molecular compounds? What does that do? Again, what's the definition? Separation. What about acids? Acids. What's the term? What? Ionization, yes. So those are the three terms. Make sure you know them. We're going to focus on dissociation today, ionic compounds, okay? When you put ionic compounds into water, for example, in this first one here, we talk about barium nitrate. When you put barium nitrate, which is a solid, by the way, all ionic compounds are solids, okay? When you put barium nitrate into water, water is able to, in most cases, with a lot of ionic compounds, is able to break those apart. They break into their ions. That process, of course, is called dissociation. So when you put this into water, you get barium ions and some nitrate ions, okay, in water floating around. So they break apart from each other, and once again, that's called dissociation. So that's what we're going to look at today. We're going to look at what's the actual concentration of those ions that are floating around in this water here, okay? So we're going to use what we call a dissociation equation for these ionic compounds, and we'll take a look at the first one here. Now, there's a few things with terminology, etc., states, and things like that, and we'll get to that as we go along here. But the first thing here is this. We need to calculate the concentration of each ion present when you take 2.75 grams of barium nitrate and you put it into 250 milliliters of water. Well, let's take a look here. Barium nitrate. Looks like that, of course. Barium nitrate. Barium's a 2+, nitrate's a 1-, swap and rub. That's an ionic compound. Okay? If you go into the chemistry room, for example, to the back room, all ionic compounds are in solid form. Remember, barium's lost 2 electrons. Where do those 2 electrons go? It has to go with, of course, they have to go somewhere. Nitrate accepts those 2 electrons in this case. So barium loses 2 electrons, nitrates each gain 1, so we need 2 of them, so that's where the formula comes from, right? When you put this into water, though, okay, we get barium ions floating around and some nitrate ions floating around. So we put them into aqueous, of course, because now they're in water. Okay. Like I said, when you go to the chemistry room, all ionic compounds, every ionic compound there is in solid form. Okay, because remember, they stick together very well. Crystal lattice structure, opposites attract, plus minus, etc., etc. You can't go into the back room, or any room for that matter, okay, in the chemistry lab or anywhere else. You cannot get a bottle of barium ions. There's no such thing, okay? There's barium solid, sure. An element, yes, you can get barium, okay? But you cannot get barium 2+ ions. There's no such thing. Because, why? Well, barium 2+ has to give off 2 electrons, right? Barium becomes more stable by losing 2 electrons. Where do those electrons go? You need something to take those electrons, right? In this particular case, it happens to be nitrate. But you can't just have barium ions in a bottle somewhere, okay? You need to separate them, basically, by putting them into water, dissociation. All right? If you look at this equation, so step 1 is always going to be write out a dissociation equation. Step 2, you want to look at this and say, hey, does this make sense? Look, for every one of these compounds, I have 1 barium and 2 nitrates, right? We need to make sure we balance this, right? Look, barium's a 2+, each nitrate is a 1-, so I need 2 of those to go with that, 2 of those, 2 negatives, basically, to go with this 2+. Remember, look over here, 2+, 2-, yes? Okay? They have to cancel each other out, because barium implies 2+, that I've lost 2 electrons. Where do those electrons go? Well, they go to each nitrate, right? So we have to make sure that balances out. So we need to, step 1, write out the dissociation equation. Step 2, we need to make sure we balance it before we do anything else. All right? Step 3 is going to be putting the information in the right spot. And I want you guys to line this up like I do today, because this will help you when we get to, well, later in this unit and unit 4 as well. We do exactly the same thing. That's always done that way. Okay, that way we know exactly where stuff is going. So we have 2.75 grams of barium nitrate in 250 milliliters of water. First of all, here's my 250 milliliters of water. Okay, right here. It's a little dirty. That's okay. That's good water. So I got 250 milliliters of water here. Here's what we're doing. This is all we're doing. We're not doing a chemical reaction, nothing else. We are simply weighing out 2.75 grams of barium nitrate. Okay, got it in my little weigh cup, or in my little beaker if you want, and I'm simply dumping it into 250 milliliters of water. Okay, that's all we are doing. So I'm weighing out a specific weight, and I'm putting it into 250 milliliters of water. Well, if that's the case, does the volume ever change in this particular question? In other words, I start with 250, and when I'm done, I still got 250 milliliters of water. Okay, so I'm going to put 250 here. I'm going to change it to liters, of course, because we're probably going to do some molar concentration stuff. I have 250 here, and I have 250 here. Okay, so whatever I dump in originally into that 250 milliliters of water, that's all I'm doing. Okay. 2.75 grams of barium nitrate. Now, if you read the questions closely, it'll tell you exactly where you should put 2.75 grams. It's barium nitrate. That's this. 2.75 grams, okay, of barium nitrate. Barium nitrate, of course, is my ionic compound. Remember, you can't weigh out barium ions, okay? You're not going to be able to weigh those out. You can weigh out the compound, barium nitrate, but you won't be able to weigh out barium ions, or for that matter, nitrate ions. Okay, you can't weigh those out. All we are simply doing is taking this 2.75 grams and putting it into 250. Okay? And what I want to know is this. What is the concentration of each ion present? Okay? What is the concentration of the barium ions? What is the concentration of the nitrate ions? All right. So what do I need to find? If I'm looking for C for both of those, what do I need for both of those? What's missing? How do you calculate C? What do you need? Somebody, anyone? C, I need N. Yeah, we need to know N for both of these. Yes? All right. We already have V for both, by the way. We know that this is all taking place in 250 milliliters. So, how am I going to find N? Well, I can tell you this. We could find the molar mass here. And little m and big M would give me N here, of course. Okay, so let's do that. Let's see, barium is 137.33. And we need 2 nitrogens. And we need 6 oxygens. So 261.35 grams per mole. And I can find N from those two. Okay, so 2.75 divided by that. And I get 0.0105 moles here. Okay. 0.0105. Now I rounded that number, but that, of course, not on my calculator, but that's up there, it's rounded. Now, you know, we need to kind of look back at this compound here. Look, for every one of these compounds, let's say I was able to take out one barium nitrate compound. When I put it into water, okay, that one compound breaks up into, that one compound here breaks up into 1 barium ion and 2 nitrate ions. Okay? Well, gee, let's say, let's go on a little bit bigger scale, because to actually get 1 barium nitrate would be pretty tough, probably. Let's go with 1,000 barium nitrates. If I took 1,000 of these compounds, counted up 1,000, I'd end up with 1,000 over here. And remember, every time we put this into water, this breaks apart into ions. Well, in this compound here, right, for every one compound, it's involved with 1 barium and 2 nitrates, right? So if I took 1,000 compounds, I'd end up with 1,000 bariums and 2,000 nitrates. Yes? True? Let's go bigger. 6.02 times 10 to the 23. Or let's say I took a mole of this. 6.02 times 10 to the 23 of these. I'd end up with 6.02 times 10 to the 23, or a mole of this, and twice here, 2 moles of this, right? Well, it turns out I don't have a mole, but I do have 0.0105. So how many moles should I get there? Probably the same, right? 1-to-1 ratio. So if I have 0.0105 moles here, I probably get 0.0105 moles of these barium ions. All right? Because for every 1 mole, I get 1 mole of barium ions. Well, 0.0105 moles would give me 0.0105 moles of barium. And how many moles of this would I expect to get? Well, once again, we look at the ratio here. For every one of these compounds, it gives me 2 nitrates, right? So times this by 2. If you want, you can put times 1 there if you want. Times that by 2, and I should get about 0.0210 moles here. Twice as many. Twice the amount, right? So look, I have N and V for both of these, and I can simply find the concentration for each one of these. So if I divide it by the volume, I get here, I'm going to do the final answer here, 0.0421 moles per liter. Okay? N divided by V, of course, gives me C. All right? And do that for the same thing for over here, and I will get 0.0842 moles per liter here. Twice as much. Okay? And that's the concentration of each ion that is present. Okay? Now, before we move on here, that's pretty much what we're going to be doing today. That's pretty much it for the most part. But is there any questions before we move on here, or before I tell you any last few things here? Questions? Anyone? We'll obviously do more examples here, but listen. So you might say, well, first of all, what do you notice about this concentration here? So this one here. And what do you notice about this concentration here? Look at those 2 concentrations. What do you notice about them? Shh. Concentrations. What do you notice about them? They're what? They're what? Double, right? So look, this is a 1-to-2 ratio, and the concentrations are double, right? Well, why is that? Well, because remember, this is all taking place, we're not doing a reaction here. We're just simply taking on a compound and putting it into water, okay? So could I have found the concentration here, for example? Can I find the concentration? When you do barium nitrate into water, the first thing that's going to happen is you're going to end up with barium nitrate, solid, in some water before it breaks apart. Very, very quickly, of course, it probably will start to break apart. But initially, you could find the concentration here as well, right? I'll tell you right now, it's going to be 0.0421 moles per liter. How would I find that? Well, look, N and V, right? C equals N over V. So 0.0421, 0.0421, 0.0842. You'd end up with twice the concentration for nitrates as you would for the barium. Why is that? Because you have twice the amount, right? Look at what doesn't change. 250, 250, 250. What is changing is the amount for each one of these ions. Look, to make this one compound, you need 1 barium, but 2 of those, right? So for every 1 compound, you have twice the amount for the nitrates, right? Twice the number of nitrates. Twice the number of nitrates, twice the amount for nitrates. So, makes sense when you think about C equals N over V. What's the only thing changing here? Well, N, the amount. V stays the same. If you get twice the amount, you get twice the concentration, right? Could you have found the concentration here and then moved that over to here and to here, for example? Sure you could have. You could do that as well, okay? And in some particular examples, you may have to do that. You might not have a choice. I do want to see this lined up, though, like so. So I want to see the equation balanced, and I want to see the information under each spot. And that's for two reasons. One, it makes my life a lot easier when I have to mark these. But most importantly is you know what you're given, you know where it goes, and you have a plan to get to where you need to go, okay? And this is really going to help you in Unit 4, trust me, because this is exactly what we're going to do in Unit 4, except we'll mix different stuff together, and it's done a little bit differently, but it's pretty much the same idea, okay? Stoichiometry. So we need to make sure that we kind of line stuff up here. We know what goes with what, okay? Today, like I said, for this here, we're just focused on what's going into a set volume of water. So here's 250 milliliters. I'm going to put 2.75 grams of barium nitrate. I dump it in. Initially, I have this concentration here. And as it breaks apart, when it's all said and done, I will get this concentration for barium and that concentration for nitrate. Barium nitrate is very soluble. You would expect to get a lot of ions. Okay? So, any questions so far? Questions, anyone? That's good barium nitrate. All right. What else was I going to say? I will tell you this. If you have a choice, what I want you guys to focus on is, and you can do C, so you could find C here and move it over, and that's fine. But listen, I'll tell you right now, if you really want to be on top of stuff, especially for starting for Unit 4, you really need to find N. Because when C works here, and it does for this and this, that's fine for Unit 3 stuff. But in Unit 4, you need to be able to find N for these, okay? So if I were you, I'd kind of get into the practice of finding N, just like I did here. So we found N, and I moved N over, and I moved N over. That's what you should try and focus on. When I do these questions, that's what I do, because that's going to help you with Unit 4 stuff, okay? So that's why I use N all the time. Can you do C in this unit? Absolutely. You can move C around. That's fine. But for Unit 4, that's not going to work. Okay? Let's look at another example here. Here we go. So I want you guys to do the following for me. A solution of sodium phosphate contains 3.15 times 10 to the negative 2 moles of dissolved sodium ions and 720 milliliters of solution. Calculate that. Well, this means, by the way, you guys want to write this down probably. So when you see square brackets like this, it means find the concentration. Okay? Square brackets implies concentration. Square brackets implies concentration. Here's what I need you guys to do for me. I want you to do a dissociation equation, step 1. I want you to balance it, step 2. So write out a dissociation equation. You can use your first example as kind of a guideline. Write out equation, balance it, and if you feel comfortable, I want you to start putting numbers in the right spot. Okay? If you're not, you can wait, that's fine. But equation and balanced. Okay, sodium phosphate. Sodium's a 1 plus, phosphate's a 3 minus. We need to make sure we swap and drop. So we need to make sure we get the right formula to start with, because if you don't, things are going to go badly very quickly and you'll never get the right answer. Okay? So first of all, very important, right chemical formula for sodium phosphate. Sodium's a 1 plus, phosphate's a 3 minus, swap and drop. Secondly, you need to break this up. How do you break it up? Well, say the names. Sodium, phosphate. Sodium ions and phosphate ions. Okay, sodium comes as a 1 plus, phosphate. You can look that up on the periodic table. Comes as a 3 minus. This will be into water now, of course. Dissociation implies you put it into water so that the ions break apart. Okay? You might say, what should I use for the symbol for sodium phosphate? Should I use solid? Well, sodium phosphate absolutely starts out as a solid. It's an ionic compound. When you put it into water, it becomes aqueous and then breaks into ions. They're asking you right here for aqueous. In other words, when it's put into water, what is the concentration? It doesn't make sense to talk about the concentration of a solid. Okay? Now, am I going to mark that right or wrong? In the big scheme of things, guys, it's not a big deal. Okay? This absolutely should be aqueous, and so should that. Okay? This here, if you put solid, I'm not too upset about that. They do talk about, you know, if we are finding the concentration, we probably should put aqueous. It doesn't make sense to talk about what's the concentration of a solid. What's the mass of a solid? Sure. What's the concentration of a solution? Yes. Okay? So, just a little thing. If you understand that, then that's great. If you don't, I'm not too upset. You'll get used to it eventually here. That's step 1, writing out the equation. Step 2, you got to balance it. You got to make sure it's balanced. Look, in order to balance this, I need, this thing's blinking here, but 3 sodiums and 1 phosphate, right? Look over here. 1 plus, 3 minus. How am I going to fix that? Well, I need to put a 3 there, right? 3 pluses, 3 minuses. They need to balance out, right? Each sodium loses an electron. I need 3 sodiums to lose 3 electrons so that 1 phosphate can grab those 3 electrons, okay? We're going to put information in the right spot. The first thing I see there is 720. Where can I put 720 milliliters of solution? I'll give you some options. Left, middle, or right. Where do you want to put 720? Left? Where else? Huh? All of them. Sure. Let's put it at all of them. Because remember, this is taking place all in one beaker. And this beaker happens to be, well, I don't know what size of beaker we have, but I do know we have 720 milliliters of water, basically. Okay? So we're going to put that for all of them. It's taking place all in the same beaker. Okay? The other thing it told you here was this. We have 3.15 times 10 to the negative 2 moles of dissolved sodium ions. Where should I put that number? 3.15 times 10 to the negative 2. Left, middle, or right? What do you think? Left, middle, or right? 3.15 times 10 to the negative 2 dissolved sodium ions. Where does that need to go? Left, middle, or right? What do you think? Paige? Not quite. Dissolved sodium ions. Left, middle, or right? It only gives you one other option now. Katie? Middle. We're going to put it right here. And we're going to put this as 3.15 times 10 to the negative 2 moles. Okay? And it tells you that right there. 3.15 times 10 to the negative 2 moles, so that's N, of course, of dissolved sodium ions. Where is the sodium ions? Right here, right? So we need to put it there. Okay? You just have to make sure you read the question closely and make sure you line them up, okay, appropriately. All right, so there's N there. All right, what are we looking for? We're looking for, square brackets, concentration of sodium phosphate. That's all together, sodium phosphate. We are looking for this, correct? It tells you right there, guys. Look, square brackets, sodium phosphate. That's what we're looking for, C. How are we going to find C there? What do we need? Well, as always, what is C? N over V. Probably would help if I knew an N here, yes? True? C equals N over V. How am I going to find N? Well, what else do we know? How can I find N? Well, look, I know N right here. Can I move that over to here? Remember, for every one of these, I get 3 of these. Yes? So, in this case, that's a 3-to-1 ratio, right? Or a 1-to-3, whichever way you want to look at it. But if I want to get from 3 back to 1 here, I need to, in this case, divide by 3. Okay? 3 to 1, so I need to make sure that that's a 3 to 1, right? So, if you give me a sec here, yeah. It's 0.0105 moles, okay? Can I find C? I know N, I know V. Sure, divide the two, and I get final answer once again here. This will be all rounded and everything. 0.146 moles per liter. Okay? That's question A. Okay? This we've just answered A. Right? Calculate the concentration of sodium phosphate. Right? So, 0.0146. 0.0146. 3 significant digits, 3 in the question. Okay? B says, what is the mass of sodium phosphate? So once again, are we talking about sodium ions, phosphate ions, or are we talking about sodium phosphate? So we want to make sure we line this up, right? Look, what is the mass of sodium phosphate that is required to do this, basically? Well, how do we find the mass? What formula does that? N equals little m over big M, yes? So we need to know the molar mass. Do we know N? Yeah, it's right there, right? So we know N, 0.0105 moles. We need to know the molar mass, sodium phosphate. So let's see, that's, somebody have that by chance? 163.94, okay? 94 grams per mole. Okay, we know N, so we can simply multiply those two numbers, right? Mass equals N times big M. So we know 0.0105 moles, and these two things here combined will give me that, right? So we multiply those together, 163.94 and 0.0105, and I get, last answer here, 1.72 grams. And that would have been answer B here for that. Okay? So basically how you would have gotten this is you would have taken 1.72 grams of sodium phosphate from the back room solid. You would have dumped that into 720 milliliters. Okay? You would have gotten this concentration here, 0.01046 molar. And as a result, you would have 0.0105 moles of solid. For every 1 mole, you end up with 3 moles of sodium ions. Because for every 1 mole, of course, there is 3 times that amount of sodium ions in that one compound. Right? There's 3 times the number of sodium ions for every 1 compound. All right? Is that good? Any questions so far? Questions, anyone? Once again, you'll notice we're moving N. Okay, that is key here. That's what your focus is today. I took this N here and I moved it over to here. And I used the ratios to do that. All right? Where the ratios come from? Balanced dissociation equation. Okay? We're going to do exactly the same thing on the next example. We're going to kick it up a little bit of a notch, but not really. Okay? This one here. When we talk about amounts, amount of course refers to moles. Well, if I wanted to actually change that, I could talk about the actual number of ions I would have by using Avogadro's number. So I might not want to talk about moles or the amount. I want to actually maybe count up the number of ions there. Okay? So once again, we know that 1 mole is 6.02 times 10 to the 23 of ions, atoms, molecules, whatever the case might be. Okay? So you got some options there. We're going to look at the next example here, and I'm going to get you guys to do exactly the same thing that you just did for me on the last one. So you take a little break on this one. How many sulfate ions would be found in a beaker containing 450 milliliters of 0.175 molar iron 3 sulfate solution. So, once again, dissociation equation, balance it, and then maybe put the information in the right spot if you're comfortable with that. So let's go ahead and do that now. You guys can keep working here, but I'm just going to write up the equation here, but feel free to keep going here. So we got iron 3 sulfate, 3 plus sulfate's a 2 minus. We need to make sure we swap and drop here, right? Brackets, 3. Now, do you want to call that a solid or aqueous? It's up to you. Okay, I'm not too upset either way, but I will tell you this. Look, it's 450 milliliters of 0.175 molar iron 3 sulfate. So they're telling me basically right now that it's a solution already, probably. Okay, we're going to take this solution. So I would probably tend to say, hey, you know what, aqueous probably makes a little bit more sense. But if you put solid, once again, for now, that's okay. All right. However, over here, we need to think about, okay, what are the two ions? Well, iron 3 sulfate. Iron 3, that tells you it's that. It's most certainly in water. Sulfate is a 2 minus, and that's most certainly in water as well. So iron 3 sulfate. Okay, you separate those two. Those two ions that you come up with. Okay, we do need to balance it. Okay, so that's part of it. Don't forget, look, 2 irons, so 2, 3 sulfates. So we need to put a 3 there. If you're not sure, then what's the lowest ratio that's going to make that neutral? Look, 6 plus, right? 2, 3 pluses, so 6 plus, 6 minus, right? They have to equal 0 because ionic compounds, when you put them together, electrons all are accounted for, right? Neutral compounds when you put them together. So we start with that. Secondly, what do we want to find? Well, before we do that, where do you want to put 450 milliliters? Where do you want? Left, middle, or right? Sure, we can put it on the right. Anywhere else? Somebody says all of them? Sure, we can do all of it too. Remember, this is all taking place in the same beaker, so, yep. And you don't have to put it everywhere. If you don't want to, that's fine. But I would probably start out with that. Okay, that's true for all this. We're putting this all into 450 milliliters of solution. So we all have this, right? Where do you want to put 0.175 molar iron 3 sulfate? Left, middle, or right? This is a little bit more important here. Where do you want to put the 0.175 moles per liter? Left, middle, or right? What do you think? Left, okay? Right here. They're telling me that this initially 0.175 moles of iron 3 sulfate. They tell you this right here, right? So we need to put it as iron 3 sulfate. If they would have said iron 3 plus ions, that's different. If they would have said sulfate ions, that's different, okay? They're saying it's 0.175 moles per liter of iron 3 sulfate. We need to put it there. You know, right away, I don't know if you guys noticed, but look, C and V, I could find N. That's probably a good thing to do, okay? Because that's what we're going to be moving around. Ultimately, what do we need to find? How many sulfate ions are in the beaker containing this? So, how many ions? I'm looking for this, right? It says how many sulfate ions. I'm only concerned about sulfate ions. Do I have iron 3 plus ions? Sure I do. I don't care, okay? This one says how many ions do we need to have there? Well, once again, what are we going to do? How are we going to get over there? We're going to use N. Could you use C? Sure you can. So could I take this and move it over to here? Absolutely. But now you have C and V and you still need to find N. So it doesn't matter when you do it, but at some point you need to find N. N is the key to these questions, right? So C and V, we're going to multiply those two, of course. 0.175 and 0.450. We get 0.07875 moles if I'm going to do it here. I'll move N over to here. To do that, though, don't forget, this is for one compound. For every one compound, I get 3 sulfates, right? So, or for every 1 mole, I get 3 moles. Or for every 0.07875, I get 0.23625 moles. And I'm going to put a times 3 there to show you that that's what I did. Okay? And I usually write arrows, and I'm going to do exactly the same thing when it gets later in this unit, because we're going to do this again later in the unit. I'm going to do it exactly in Unit 4 too. Okay? So, there we go. I need to figure out how many ions there are. And I know what I'm not looking for. I'm not looking for this, right? That's not what I'm looking for. I'm not looking for the concentration. It didn't ask me to find that. Could I find that? Sure, I could. Okay. Do I have to do all that work to find the concentration? Probably not, because I already know the concentration there. I just move it over, right? Times 3. Done. I'm not looking for the concentration. I'm looking for how many ions. If you sat down and counted them, 1, 2, 3, how many would there be? I'll tell you right now, there's going to be lots. Because 1 mole is 6.02 times 10 to the 23 ions, atoms, molecules, whatever the case whatever it applies to, right? So 1 mole is 6.02 times 10 to the 23. Well, I guess 0.23625 moles would be about, final answer, 1.42 times 10 to the 23 ions. That's how many ions I'd actually have. So you'd have to sit down and count those all up, but that's how many sulfate ions you'd expect to see there. Okay? 1, 2, 3, 4, count them. Lots, right? Okay? So that's how many ions you'd expect to see. Any questions on that one? Okay? As with most things in chemistry, if we can do it frontwards, we can probably do it backwards. So we'll take a look at one of those real quick, and then we'll be done. Okay? Let's do the same thing for this, guys. Let's get an equation for this. That's where you got to start with all these. Balance it, put the information in the right spot. Remember, you're looking for square brackets here. Alrighty, so we're going to start with potassium dichromate. Potassium's a 1 plus, dichromate's a 2 minus. We need to make sure we swap and drop. So 1 plus, 2 minus. Once again, do we want to call that aqueous or solid? Once again, I'm not too upset, but if you look over there, it does say calculate the concentration. If we're looking for concentration, probably should be aqueous. Concentration is solution, right? And it even says that actually right there. So probably aqueous is a good thing to put here. What does potassium dichromate break up into? Well, it breaks up into potassium ions and dichromate ions. Okay? Potassium dichromate. We need to balance it. Do not forget to balance it, because that could turn out to be a nightmare if you don't. You'll probably end up with, half as much or twice as much as what you need. So we want to make sure we balance it. Where does 625 go? Probably everywhere, yeah? So we can say I got 0.625 liters here, 0.625 liters here, 0.625 liters here. Okay? So this is all taking place in 625 milliliters. We have 7.18 times 10 to the 22 potassium ions. Where does that need to go? Left, middle, or right? What do you think? Where? Middle, sure. It tells you right here, look. That many potassium ions, right? It didn't say potassium dichromate, it doesn't say chromate, dichromate. This is potassium ions. We need to make sure that goes right here. 7.18 times 10 to the 22 ions. Now that's not N, okay? That's actually the number of ions. We need to use that to get N. Ultimately, what are we looking for? Once again, look at the question here. Square brackets, concentration of that. That's right here. So we need to find the concentration there. How are we going to do that? We need N and V, always, right? How are we going to find N? Well, let's find it over there. Move it over, right? Find N, move it, all right? Well, I know that 1 mole is 6.02 times 10 to the 23 ions. if I had 7.18 times 10 to the 22 ions, how many moles does that work out to be, right? Make sure we line stuff up. Moles, moles, ions, ions, right? Make sure we keep it the same. When you do this, there's a division here, of course. The proper way to do this is take 7.18 times 10 to the 22 divided by 6.02 times 10 to the 23. Do not forget to use brackets, please, right? Otherwise, we're going to get wrong answers, e to the 45 and e to the 44, and that's silly. And when you do that, you should get 0.1187 roughly moles. Okay? Once again, you don't want to round it. We're not done yet. Oh, sorry. I think I'm a little bit off there, aren't I? Sorry, I typed in the wrong thing here. Let's try that again here. My bad. Yeah, 0.119, sorry. 0.119 moles. Okay? We know how many moles we have for that now, so we know this, right? How am I going to get there? Well, look, once again, 2 to 1 ratio. Divide by 2. So divide by 2, and I get about 0.0596 moles. There. I have N, I have V, we divide them, and I get, finally, moles per liter. Concentration of potassium dichromate that I would have started with to make this, basically make this solution. Okay? Questions, anyone? Questions? All your questions today will be similar to that, of course. Other than that, I think we've pretty much done every kind of question we'll give you with this.